Hi everybody! Welcome back to Chem 161. We'll just let the music finish out here, because it's almost done. There we go. What are we doing today? We're going to finish Chapter 2, because we really need to do that. And then we're going to start Chapter 6. I know that's a weird chapter order, because, well, it's not in order. But I personally think that the content makes the most sense if we do it this order. And also, the last chapter is kind of the chapter everyone forgets anyway in the class, and if we end the class with Chapter 6, nobody's going to remember how to do molarity, and I'd rather you forget how to do, like, balloon diagrams for orbitals later. Or geometry. Not geometry, we're going to do that earlier. So let's just get started. We left off near the end of Chapter 2, right here at the mole. And the mole is a concept that we spent, like, the majority of 140 discussing. So if you are coming from 140 or high school chem, you remember what the mole is. So the mole is this number. 1 mole of something is 6.022 times 10 to the 23 of that something. That is a humongous number. It is impossible to illustrate how big that number is unless you have to actually write it out. And if you did actually write it out, there it is. That's absurd. Now, obviously, not an exact number. We only have 4 sig figs in this because we only know about this place for this number as written. You can write it with more sig figs. I think the next few digits are like 315 or something like that. But generally speaking, 4 sig figs is going to be enough for our work anyway. So we're going to use that number. If you have not memorized Avogadro's number by now, you will, because you will have used it so many times in the chemistry series. But to be fair, we're not really going to use it terribly much in Chem 161. You're going to come back to that a lot more at Chem 162 when you do all the stoichiometry. Now, by definition, a mole of carbon-12 is Avogadro's number of atoms. A mole of carbon-12 is also 12 grams of carbon-12, which is what we defined when we were talking about mass spec. So there you go. Those relationships right there are very important for the foundation of how we weigh stuff at the atomic level. Now, if you want to use a different element, instead of carbon, you just need to substitute out this number here for whatever the mass of the isotope is that you're looking at. Or if you just want to use all of the isotopes collected together as just a generic element, you could take the atomic mass off the periodic table and replace it there, and then you're all set. The other numbers don't change. 1 mole is always the initial amount that we're going to refer to, and in a mole there are always Avogadro's number of things. Alright, so you can write 3 relationships with those things by just picking any 2 of these 3 items and then setting them equal to each other. And again, if you want to just use so we could call it the molar mass. Atomic mass is also the same term. You could just replace the molar mass for any element that you want in this space right here. Or right here, because they're the same. So we're going to be using that to solve various problems in this section. And then we're going to apply all of that when we get to Unit 6, which is concentration and solutions and stuff. Alright, so if you want to look up the molar mass of iron on the periodic table, you just find it on the periodic table. I already have p-table open. Let me see if I can find it. No, I can't. Hold on. OBS is very powerful, but if you minimize things, it is essentially hidden from it. Oops, All right. So if you look at iron right here, boop, there it is. And you see this number right next to it, 55.845, that I'm highlighting. That is the atomic mass of iron and AMU, but it's also its molar mass. That's the number of grams per mole of iron. And you could do that for any element that you want. Now we're going to be using these relationships to do chemical calculations. And a lot of these calculations are going to just be review, so bear with me because we're going to go through them. If you want to determine the molar mass of a compound, you could just add the molar masses of stuff together on the periodic table. So again, we can go back to the periodic table here. This doesn't fit, unfortunately. So I need to make it even smaller so you can't read the numbers. There we go. So now we can look at, if I take sodium here, which is 22.99, and then chlorine, which is 35.45, those should add together to give you something that's approximately 58 or so. And when we go back to this problem, you can see, like, oh, you can punch those two numbers in your calculator, and yeah, you get 58.44. I'm going to assume that everybody knows how to do that, but if you don't, let me know, and we can go over a few more examples. Same thing with sugar. I could just add up all these numbers on the periodic table here. So I could take whatever carbon is and times it by 6, then whatever hydrogen is and multiply it by 12, and then whatever oxygen is and multiply it by 6. There's got to be an easier way, and there is. And that's where we go to Lentech for. I don't know when I started using Lentech, but Lentech is super useful. So at some point you just get sick of writing in formulas for this stuff, and you decide, oh, I'm going to just leave it to an online calculator to do this for me. If I could type, that would be nice. There we go. And there's the result. So the molar mass of this molecule that I typed in is 180.16. And you could do whatever you want to here. I could type in my name, and it would give me a molar mass, because tungsten and einsteinium are things. Ironically enough, you cannot do chemistry. Because you get to M, and you're just like, what do I do with M? There's no element that has M. So, oh well. All right, let's do some calculations here. So I can convert some number of moles to the number of particles that are in there. I do want to clarify that the word particles here is used as a catch-all. So this could be atoms, or it could be molecules. It could also be formula units, which are useful if the substance is ionic. All of these are represented by particles. Basically, this box is for counting. How many of this thing do I have? Down there on the bottom, grams, very obviously how much mass something has. We know what grams are. So we can use these two relationships to figure out any quantities that we want to. And so we're going to do some very basic calculations here, just to get you in the habit of using Avogadro's number and the mass-mole relationship, because we're going to use it again in Chapter 6. But we're not going to actually do stoichiometry in Chem 161. We're going to do that in 162. Oh, it's very dark on the screen because, again, things that are minimized. OBS doesn't know what they are. That's probably good, because I could just minimize things out of the way and then you don't have to see them, but it does keep them on the screen. So. My decimal point didn't appear there. I need to zoom this in, I think, so my resolution isn't super grainy. All right, so we're going to solve this question. How many moles of silver are there in 154.1 grams of it? Now, if I am given a quantity of silver in grams, I could turn that into moles of silver. No problem. I would just use the molar mass. And so the relationship here would be some number of grams of silver is equal to a mole of silver. And we would need to go to the periodic table to find that. So let me get the periodic table on the screen here. I have to capture it again. I have no idea where this will capture, so... There's silver right there, so you could see it at the bottom. So 107.87 grams per mole. So we'll get rid of this. Boop. And that's the number of grams in 1 mole of silver. So now we can come over and write a relationship and set up the units so that they cancel. Well, I don't want this, so I got to put something that matches right there, right? Pre-canceling my units, but, you know, as you do. All right. Now that I've got the units that I want as my answer, we can run the numbers. So in a 1 mole, there are this many grams. And then it's just a matter of punching it in the calculator and you're all set. And I got this, 1.42857, so I'm going to round that to that. Then we can consider sig figs. The lowest number of sig figs in these results is 4, so my answer should have 4 sig figs. Remember that whenever you see 1 somewhere, those 1s are infinite. In exactly 1 mole, there are approximately 107.87 grams. All right. Let's do the same type of question here. I don't want this window extending off of the screen there. There we go. How many atoms are in a sample with this many grams? So now I just got to do an extra step, don't I? Oh, my Photoshop messed up. Hold on. So now that I have grams turned into moles, I can just turn moles into particles of silver. Now, we're working with atomic silver, so I'm actually going to write the word atoms here instead. And then what's the relationship between moles and atoms? Well, a mole of anything is Avogadro's number of that thing. So now that I know the entire relationship between all 3 things, I can then go down here and say, okay, well, if I have this much silver this time, well, gotta get rid of this unit, so I gotta put it down here to cancel it. Could you skip this interstitial grams to mole to atoms, just go straight grams to atoms? Yeah, you could. Later on, though, when you're doing calculations in stoichiometry, you're going to be turning everything into moles anyway, and it just becomes habit. So now we'll run the numbers. A mole is still 107.87 grams of silver. And there's Avogadro's number of atoms in a mole. So grab your calculator or Wolfram Alpha and put all this stuff together. When you're doing calculations with exponents that are this large, you kind of get forced into using the EXP button or EE. Make sure you're using it correctly. You should get this as your result. 2.191 times 10 to the 24. And that should have 4 sig figs because of the number we started with, and also because of Avogadro's number. If you got a number that's like 10 to the 23, but the first number is correct, 2.191, what you're probably doing is using the EE or EXP button wrong. If you have a calculator issue, I've seen every calculator under the sun, but trying to describe what your model calculator is to me, probably not gonna it'll take a lot more effort than if you just take a picture of your calculator. So if you have calculator issues and you don't know what's up, photograph your calculator in some way and send it to me over Discord or email, and I will look at it and I'll immediately know how to enter in what it is that you need. All right. So those are some basic calculations that we can do using this concept of grams to moles. Let's do some stuff with molecules here, because there are a few extra steps that we're going to do along the way. And that sort of practice calculation it always behooves us to do that. I'm in the wrong window. There we go. So let me clear all of this out. There we go. All right, how many molecules are present in 9.213 grams of C4H10? So I am starting with grams of C4H10. Actually, let me do this in a different color, because I want purple to be my conversions here. And I need to get to molecules. I'm going to go through moles anyway. You don't have to. You could go straight from grams to molecules, but I personally think that this is the way to do it. And then molecules. We need to get to Lentech. That's the wrong window. There's the right window. So we'll go like this. And hopefully it's on the screen somewhat. I could just scroll this down. All right. So we're going to type in C4H10 and hit enter. And it tells us that in 1 mole of C4H10, there are 58.12 grams of C4H10. So we'll write that down in purple here. So 1 mole C4H10. I didn't put enough space over here. I guess I could do this. I've already forgotten that number. 58.12. I'm glad I checked. And then down here, a mole of anything is Avogadro's number. Of that thing. That should be a decimal point. All right, so now let's set up the dimensional analysis. So we've got 9.213 grams C4H10. So we got that, and then we can cancel out moles with molecules. And then run the numbers. So in 1 mole there are 58.12 grams. And in 1 mole there are Avogadro's number, molecules, and so I just punch it all in the calculator again. I got 9.546 times 10 to the 22. There you go. Not terribly difficult to do. Now, later on in 162, we're going to show a different way to do this calculation. And by this calculation, I mean the next question that's popping up on the screen here. Now, if I know how many hydrogen atoms there are per molecule, I could figure out how many hydrogen atoms there are in a collection of molecules, right? Because if I know this number right here, I could then say, okay, how do I convert to the number of atoms? Well, I would just look at the ratio in the formula, right? I could say in one molecule of this, oops, there are 10 atoms of H. So that means I could do this. Well, I have the number of molecules that I've got of C4H10, and in one molecule of C4H10, there are 10 atoms of hydrogen. As long as the units cancel out, the problem should make sense to us. And this times 10 is just the same number, times 10 to the 23. So you could calculate the number of parts within the whole this way by getting the number of molecules. This is not really a method that's used super often. Most of the time what people would do is, if you know the number of something, you would convert to moles, then use the mole-to-mole ratio, and then go back. But if you have a number of particles, this does make sense, because moles and particles are both a count of something. And so you could skip the interstitial step and do it this way too. The only reason that you could not do this with a different approach would be if you were using grams. Because grams are not a counting approach. 1 gram of something is not the same as 1 gram of something else. As opposed to 10 units of something is the same quantity as 10 units of something else. Alright, I think that might be everything that we really care about for the mole. Yeah, that's the last slide. Okay, so I'm going to give you these 3 problems to try. There's actually 4 problems there, because I can't count. I missed a dot. If I give you a balloon of helium, and there's 19.4 grams of helium inside the balloon, that's a lot of helium, by the way. How many moles are there? How many sodium atoms are you allowed to eat per day? If you're allowed to eat 2,400 milligrams of sodium. Here's an aluminum sphere with this many atoms, and here's its density. What's its radius if this is the volume of a sphere? Assume it's a perfect sphere. And that the formula, the 4/3 is exact. Pi is not exact, of course. That's a rather tricky problem. I love to throw shapes and conic sections and random objects that have a formula and say, I want a solid platinum cube. It must be this long. How much will it cost? Like, those sorts of problems you can do now. So go build me an aluminum sphere. And then 500 milligram sample of ibuprofen, because this class gives you a headache. How many molecules are there? How many carbon atoms? Do those 4 problems. Type your answers in the chat. Type anything in the chat, really. It's lonely. Hello? Is anyone there? Maya's not even here. Like, I'm just talking to myself. So do these problems, and we'll go over the answers together in like 6 or so minutes. How are we doing? Let me know if you have any questions. Keep putting those answers in the chat as you get them. That's been a preview of what I have to deal with. Maya says hello. All right, 2 more minutes. We'll go over the answers. All right, let's go over the answers here. So I'm going to move this over here. The second I started talking, Maya started meowing again. Maya's like right down, not quite at my feet, more like my ankle, I guess. She's just sitting there, but I gotta move the chair forward, so you gotta move, Maya. Yeah, you're a cat. Yeah, you gotta move though. Yeah, you are a cat. Yeah. Okay. You must be constantly petting Maya, or else she gets sad. All right. So, how many moles of helium are in the balloon if you have this many grams? So, that's a simple conversion. We know that 1 mole of helium is, and I'm just going to grab my periodic table off my table here, 4.0026 grams of helium. Ran out of space. There we go. That should be a 2. Everyone says hi to you, Maya. I don't know where she went. She must have left. No amount of attention is enough for Maya. So she's such a happy cat that she's just like, hey, you're doing blank, where blank is anything. Wouldn't you rather pet me? And most of the time it's like, no, I have to work, Maya. All right. So how many moles and how many grams? Well, we have all that information over here. So we'll just fill it right in. And we'll do the math. 19.4 divided by 4.0026. I get 4.8468 moles. So I only want to keep 3 sig figs. So, because this is 3 sig figs, so our answer should have 3. This is 5, actually. There you go. So that's the first problem. All right. How many atoms are in 2,400 milligrams of sodium? Now, obviously, for all of these problems, we've been using grams of stuff. So starting with milligrams, you're going to have to immediately go from milligrams of sodium to grams of sodium. That's easy enough. Just divide by 1,000, right? We can all do the metric system. But once you get from milligrams to grams, you can then turn it into moles. And you can turn moles into atoms. I hit the wrong button. There we go. So, how many grams are there in a mole of sodium? I didn't need to Alt-Tab. I need to actually pick up the periodic table on my desk. I tried to Alt-Tab to go to the periodic table. That is this thing that I'm holding in my hand. Has anyone ever done that? I don't think I've ever done that. That's just, like, really weird. So, 1 mole of sodium equals 22.990 grams of sodium. I did not try to Alt-Tab to put the periodic table back on my desk, thankfully. And then 1 mole of anything is the same as Avogadro's number of atoms of that thing. There you go. Oh, I missed that message, so. All right, so I'm going to immediately just start with grams. So that would be 2.4 grams of sodium. Not 2.400, because 2,400 is written only as 2 sig figs. And so we'll turn grams into moles. Is it okay to round to 2 decimal places on grams per mole? Yeah, it's totally fine. What's important is that if you are using a number that is small, have at least 4 sig figs. I know Samita is, I believe that she says, hey, you only need to just report the 2 decimal places and then everything works out. In like 95% of cases, that is fine. Helium and hydrogen are the big offenders because they're the ones that are just so small. So if you only get 3 sig figs for your molar mass, you're going to limit your precision. So try to have 4 sig figs in any molar masses that you do. I think things like Lentec and stuff like that will only go to 3 sig figs or 2 decimal places anyway. So I'm a fan of just use all the digits that are given to you, even though almost none of them matter past like 3 or 4, because that precision gets thrown away anyway. I don't know if Samhita tells you guys that, like, at some point we get towards the end of Chem 163 and starting Chem 261, and it's like, yeah, we don't give a shit about sig figs anymore. There are so many other important things, but at this level we do care a lot about it because this is a foundational class and you use a lot of this stuff for other classes. I didn't cancel my units out, but there you go. I'm not sure how sarcastic I guess she is about it. I know that Samita is a very sarcastic individual because she and I are very similar, it turns out. How many sig figs? Oh, I only get 2. So 6.3 times 10 to the 22 atoms of sodium. This is what you get. Cannot have any more than that. If you eat more than that, you will die. Dun, dun. No, you won't. I eat so much sodium per day, you guys. I cannot explain. And yet my blood pressure is low. So I'm very lucky. Like, I'm overweight, yeah. But I love salt. Salt is probably my favorite thing. I don't really like sugar. Like, I don't like sweet stuff terribly much. Sometimes you get sweet cravings. It's like, I want cookies, and nothing's gonna stop you. But 95% of the time, I'm just like, oh man, if I have a choice between sweet and salty food, I always pick salty. I'm told that that's common as you get older. But I know plenty of people who are like in their 50s that have sweet teeth, so. Alright, so problem number 3, I have an aluminum sphere. So I'm going to actually draw a little picture of this. So here's my sphere. And we know it's a sphere because I'm going to put a shadow next to it. And we're gonna have the light reflecting off of it. So there we go. There, it's a sphere now. Alright, and it has 8.55 times 10 to the 22 atoms of aluminum. And what is the radius? So, whoop. And we also give you the density of aluminum. Is it 2.7? Yeah. Alright, how the heck do you solve this problem? Well, the first step is what quantity are you given to start with? And I'm going to do all my dimensional analysis stuff up here. So I give you the number of atoms of aluminum. From that, you can get the number of moles of aluminum. That's pretty straightforward. And from moles, you can get the number of grams of aluminum. And you go back and forth between these quantities all you want. But how do I get to radius? Well, if this is the formula for... Is it 3? It's 4/3. Okay. If this is the formula for radius, there's what I need. In order to get radius, I need the volume. Well, I can relate mass to volume by using density. So by using the density, I could get the volume of the aluminum. And if I know the volume of the aluminum, I can get the radius of the sphere. So let's write out all the relationships. So in a mole of aluminum, there are Avogadro's number of atoms. And in a mole of aluminum, there are... I almost alt-tabbed again to pick up the thing off my table. There are 26.982 grams of aluminum. And again, I'm just writing all the numbers that I have. If you just stop right here, that's okay. What's the relationship between grams and volume of aluminum? Well, 2.70 grams of aluminum is a cubic centimeter of aluminum. My hair is itchy right under my headset. There we go. And then the relationship between volume and radius is just 4/3 pi r cubed. So we're going to do this for our dimensional analysis, and then we're going to take the result and we're going to put it in this formula. Although I should rearrange the formula so that I get it to equal the radius, because now I can just plug in the volume into that. And then 3, 4, pi, and cubed root are all numbers or functions. So that's easy enough to do. So let's go down here and do that. All right, so I'm going to turn atoms of aluminum into moles, because I got to get rid of that. And then I'm going to turn moles into grams. And then I'll turn grams of aluminum into cubic centimeters. And so that's going to be equal to the volume, which I'm going to put over there. So let's go get those relationships. I don't actually need to look this one up because that's Avogadro's number. That's the same every time. Grams of aluminum per mole is up here. It was 26.982 grams per mole. And then the density of aluminum was 2.70 grams per cubic centimeter. So we'll punch that in the calculator. 8.55 times 10 to the 22 times 1 times 26.982 times 1 divided by parentheses 6.022 E23 times 2.70. I get 1.42 cubic centimeters. Not very large of a sphere, huh? But that makes sense because we're using less than a mole of stuff. And a mole of aluminum would only be 27 grams or so, which would only be about 10 cubic centimeters. Okay, well, if this is the volume, I can now put this into the formula. So cube root 3 times the volume divided by 4 pi. Now, you can punch this into Wolfram Alpha. You could use your calculator. Any method works, but really what I'm going to do is I'm going to put all this in parentheses. 3 times 1.42 divided by parentheses 4 times pi. And then I'm going to raise that to the power of 1 divided by 3. Because raising it to the power... Remember that this is true. I don't know if you could see that. Let's put this in purple. So if you want to cube root this, it's the same as doing this, right? So if you don't have a cubed root button on your calculator, you can always just use the power of exponents. There's our sphere. It's some 7 millimeters thick. Or 7 millimeters in radius. So apparently this is like a little ball bearing that we made. Alright. That's the challenge problem for the set. Oops, that's not the button I meant to hit. I meant to scroll. So we're going to go all the way back up to the top, and we're going to do it again. Boop. Alright, so we got ibuprofen here. So we have milligrams of ibuprofen. I'm going to abbreviate it like that. Just like before, we need to work in grams here. And then we can turn from moles to molecules. And then once we know the number of molecules of ibuprofen, you can then determine the number of atoms of carbon by looking at the formula. So let's write these relationships out real quick. So grams per mole. So first we got to go to Lentech and type in the formula. What do I have here? I have C13, not C132, oops. H18O2. I didn't hit enter, did I? Yeah, okay. So in 1 mole of ibuprofen, I've already forgotten the number, 206.28 grams of ibuprofen. And then something obvious thing, Avogadro's number. And that's all we need to get to the first answer. So let's do the first answer real quick. So I have 500.0 milligrams. So I'm going to write that like this. Just to skip that first conversion, because we can all turn grams or milligrams into grams by now. We'll turn grams into moles. And now we can just run the numbers, because this will give us the first number that we need for the problem. So how many grams are there per mole? 206.28. And then how many molecules are there per mole? Avogadro's number. And what number do we get when we type that in? I have 1.460 times 10 to the 21 molecules of ibuprofen. And then for the second problem, how many carbon atoms are there? Well, in 1 molecule of ibuprofen, there are... Where's the formula? C13H18O2, so there must be 13 atoms of carbon. So I'm just going to take this number and functionally we're going to multiply it by 13. Because in 1 molecule there are 13 atoms. Oh, atoms of carbon. So whatever's in my calculator times 13. 1.898 times 10 to the 22. All right. Now, even if you could not do all of those problems, hopefully seeing that jogged your memory, because I'm certain everybody has done calculations of this nature to some extent. We're not going to get into too much more detail. I mean, I do really like my shapes, so you'll see problems like that. But we're not really going to do much stoichiometry in this class, just because the whole point of atoms first is to talk about the atoms first. So we're going to do all of the conceptual things. We're going to do chapter 3 is what we're going to do. We're going to talk about the physical nature of atoms and why electron configurations are what they are, and so on and so forth. And we're going to do all that before we go to start doing analytical work. So we're going to do all the concept stuff first, which is the rest of what this class is really going to be about, with the exception of chapter 6. So, all right, you can read the chapter 2 summary on your own time, but here's the first bit. There's the next bit. And then there you go. Now, if you do write a program for all of these calculations, You're probably reinventing the wheel. I'm sure that they exist somewhere. Just don't make a mistake. As long as you trust your knowledge in programming. But I mean, that is an effective way to oops. Oh. Okay, there we go. That is an effective way to study, actually, is programming stuff, so. Alright. I don't know why I'm getting this set up here, because we're going to be taking a break. Actually, we're going to take a break right now, so let's do the break first. I will get the Chapter 6 slides set up. Chapter 6 is much shorter. For whatever reason, the first 3 chapters are super long. 4 is pretty long, and then 5 and 6 are like afterthoughts, so. So you might be thinking like, man, we're already at week 4 and we've only finished 2 chapters and there's 6 total. We're never going to finish. No, we're totally good. All right, so I'm going to hit start the clock. Go take a 10-minute break. We'll see you in a little bit. Alright, we're back. Let me turn the music down here real quick. Alright, you can see on the screen there I've modified the first slide of chapter 6. So I put this slide on the first slide of chapter 6 because at the end of chapter 3 is naming stuff. Is it the end of chapter 3 or is it in chapter 4? I don't remember. It's 3 or 4. Somewhere in there we do nomenclature. And we start using polyatomic ions, and this is like way advanced warning because we're not going to get to this stuff until like week 8. But in person, I tell my students, like, you got to know these things. Like, I'm not going to give you a chance to be like, okay, it's coming. You got to know it next week. Now you got to know it tomorrow. Like, nope, you got to know it in the future. And then we're going to start using it. But hey, it's an online class, right? So just have this list handy. The list that I show you is the same that I showed in 140, if you took 140 with me. But it is also the list in the OpenStax textbook on page 172. It does go on to the next page for what it's worth, so if you're looking through the textbook. Here is that list. I have also added extra ones that I have put little asterisks next to because they are biologically common. So, like, knowing what phosphate is and phosphite, totally in your interest to do that. Just in case you get those mixed up in some situation where it matters. And we really don't want that. We don't want you to mix up phosphate and phosphite. There are some that have multiple names. Either name is acceptable. You see them in parentheses there. I prefer the bisulfite names because they are just shorter. It's easier to type, but if you use either one, it should be okay. There's the rest of them. The ones that are starred on the right are very simple to learn once you know all the chlorates. And the chlorates are in your text, but the bromates and the iodates aren't for some reason. Worth knowing. I've used sodium bromite for a specific reaction in the science fair. So, like, it's odd where these things come up. Yeah, you can put these in Excel if you want to. I mean, you could also just print screen or bookmark or print the slides or do whatever. Like, you're not going to memorize these. Who am I kidding, right? I would like for you to memorize them. When you get back in class in person, I'll be like, did you memorize them? I hope so. And everyone's going to look at me like, yeah, we memorized them because you told us not to. This is your fault, Wes. Whatever, dude. All right. We actually don't do the back half of chapter 6. So this chapter is a lot shorter than it seems. So we don't do balancing chemical equations. That's chapter 7. I'm going to leave Mark to do that for you. Or Mark or Valerie or whoever's teaching 162. We are just going to look at empirical molecular formulas and then molarity. Molarity is the important one here. Once we've done molarity, I can talk about the lab. So we'll probably finish this chapter tomorrow. So let's go through a few different ways of expressing concentration. By I don't know where I wanted to go with that. The whole point of Unit 6 is just concentration. Like, we're going to talk about how to express formulas in various different ways. So, first is percent composition. Percent composition can be done in a number of ways, but the formula is generally the same. The difference is just what unit you choose to put here. So, this is percent by mass. And I'm going to write that right here. So if you take the percent by mass of something, you are finding the mass percentage of that something in the total. So maybe you want to know the percent of carbon in carbonate, for example, or in CO2, or in anything that contains carbon. All you do is take the mass of whatever it is you're looking for, divided by the mass of the compound times by 100%. That's easy enough to do. So let's do an example here. So I have a mineral of some sort, and it contains iron, sulfur, and oxygen. I have decomposed it down into its constituent elements, and these are the masses that I got. What's the percent composition of the mineral? Well, the first thing I would need to do is figure out what the total mass of the mineral was. So I'm going to add all these together. 17 and 4 is 21. 7, 13, 26. Okay. So that looks like the total mass, if I did that right. Now, the percent mass of, we'll start with iron, would then be the mass of iron divided by the total mass, those go away, times 100%. And I got 26.5%. Easy enough, right? These should be pretty trivial calculations, so we'll do the same thing with sulfur. Oops, I didn't times by 100%. I didn't type that in correctly. There you go. I get the same result anyway. That's okay. 44.6%. And then finally for oxygen, I could do 17.4 grams oxygen divided by 60.1 grams total times 100%. Or I could just say 100% minus the percent of sulfur minus the percent of iron, right? So 100 minus 44.6 minus 26.5 is 28.9. Because all percentages have to add up to 100, yeah? Now, if you did do the calculation, I'll throw it in the calculator just to check. 17.4 divided by 60.1. I get 28. I get 29.0. So obviously there's some error, regardless of which method that you pick. But that's what sig figs are for anyway. The last digit is supposed to be estimated. So you're going to be off by 0.1 in the last digit, regardless of what method you pick. And that error is already assumed because of the nature of how sig figs work. So whether you reported to me 28.9 or 29.0, your answer is reliable and correct. All right. Let's do another one here. I gotta clear this off the screen here. What's the percent composition of aspartame? Now, how do I do this with molar masses? Well, it's actually not that much different. I'm going to show you the rigorous way, and then I'm going to show you the easy way. So the percent carbon would be the mass of carbon divided by the mass of the total. Now, what is the mass of aspartame? Well, I didn't give you an amount, did I? I didn't give you a percent. In fact, we're trying to solve the percent. So what do? Well, we know what the molar mass is, right? You could go to Lentech and type that in. So I'm going to do that really quickly. If I can find the right window. There we go. So C14, H18, N2O5. Wes, why aren't you showing the window on the screen? I'll tell you why in a second. All right, so the mass total would be, again, I've already forgot the number, 294.30 grams per mole. What's the mass of just the carbon? Well, that would be whatever the molar mass of carbon is. times how many carbons there are, which is 14. So of the 294.30 grams per mole, 12.011 times 14 grams per mole of that is just carbon. So that should be our mass percentage, right? How many sig figs do I get? Like 5. Wow. 57137. And this is just an exercise in busy work at this point, right? Like, if I did this for %H, it would just be, there's the mass of 1H times how many there are over the total. So I can do that. And I get 61645. There's gotta be an easier way. And it turns out, yeah, there totally is an easier way. And that is, once again, go to Lentech. Look, there's the answers. They're right there. Ta-da! Lentech does it for you. So, like, why do all this? So you saw that our answer, 57.14 and 6.16, those are the numbers that we got, right? Yeah, there they are right there. The only thing that Lentech doesn't do is it only goes to 2 decimal places. So you're not going to get as many sig figs. So if you don't care about that, then great, you can get the result and just report it and you're all set. If you're just checking your answers, then here's a great way to do it. And you can get the percent by mass of, of anything you want. I don't know why I had to yawn and stretch there. So, yeah, so there's the answers to this problem. So nitrogen would be 9.52, and oxygen would be 27.18. Work smarter, not harder, right? If you're going to look up the answer, at least understand what the answer is. And we've done this formula 4 times already. Like, we understand how it works. So no reason to do it anymore. Just like I'm not going to make you add and do the molar mass of something over and over and over and over. All right. So that's mass percent. Any questions, let me know. Not difficult to do. Now, we talked a lot about how formulas were determined with the law of definite proportions and the law of multiple proportions in Unit 2, earlier on in the quarter. We're going to do some basic formula analysis here to determine empirical formulas of compounds by analyzing mass percentages of substances and also molecular masses using a mass spec. Now, figuring out the formula of a molecule would be really trivial if we could grab one molecule and just use our atomic tweezers to pull it apart and be like, okay, well, I pulled 6 hydrogens off and 5 carbons. There's the formula. Unfortunately, we can't do that. And the reason for that is because we don't have any device sensitive enough to isolate single molecules and then disassemble them and then count the things that are present. You get too many molecules. We're too clumsy. Now, when you determine the formula of any compound, and formulas depend on number of atoms, the best way to do this is to just combust or react or do whatever to a large sample, figure out the number of moles, and then work from there. On the screen, I have a picture of some compound that has carbon and oxygen in it. And you could assume that, like, I decompose some number of molecules. And this is the result that I get. I have these bins that I just collect carbon and oxygen in. Now, you could tell right away by just looking at the picture that there's twice as much oxygen as carbon. So the ratio of these two things must be 1 carbon to 2 oxygen, or CO2. So carbon dioxide would fit this pattern. However, so would something that looks like this, or this, or this. So we can narrow down a family of the molecules because we would know that this is not the compound. We also know that this is not the compound because those would give a 1-to-1 and a 3-to-1 ratio, right? So the empirical formula is the simplest ratio that you observe here. And in this case, that ratio is 1-to-2. The empirical formula tells you the ratio of atoms to each other, and thus gives you a selection of possible molecule formulas that this substance could be. It eliminates a lot of work for you, but it doesn't definitively tell you what the formula is, because it could be any of these. And if we don't know how many molecules we're reacting, we just don't know what the answer will be. We need to do an extra step. All right. So again, that's what the empirical formula is. Now, if I give you a formula, you should be able to look at it and say, oh, is that an empirical formula? So if I say, oh, okay, C2O4, is that an empirical formula? Well, no, you could divide out a 2, because they both have 2 in common, right? Is CO2 an empirical formula? Yeah, there's no number that you can divide out. All right, so let's do an example here. Let's suppose that you have done some sort of elemental analysis, and you've obtained a compound that has C's and H's in it, and you know that the compound has 1.17 grams of carbon and 0.287 grams of hydrogen, and you want to know its empirical formula. What do? Here's how you do this. All right, so I know that these are the quantities of stuff that I have in my sample. Now remember, molecules have formulas that come from numbers. Grams do not relate number of things that are in there. They represent masses. So we need to turn these into things that represent numbers. And that something is moles. So if I figure out the number of moles of carbon here, I multiplied. Whoops, that's not right. I was like, that's a really big number. I was expecting a small number. 0974. We're going to do the same thing with hydrogen. All I'm doing is turning stuff from grams to moles. 2.288. No, 5. Like, totally skipped a number in the middle there for some reason. There we go. All right. And so what this tells us is that we would have two piles, a pile of carbon that has 0.0974 moles, and a pile of hydrogen that has 0.285 moles. And so what I'm going to do is I'm going to just put these together and make a formula. And you might say, that's the stupidest looking formula I've ever seen. For one, formulas can't be fractions, and for two, who the hell uses decimals, right? So we're going to call this the pseudo formula. It's not a Linux command. It's not that type of pseudo. It's a pseudo formula because it's sort of a formula. What we're going to do to make it a formula is we're going to force one of the numbers to be 1. And the way that you make any number be 1 is you divide it by itself. So we're going to divide by the smallest number. And in this case, that's this number. So we're going to divide both numbers by that. And what I should get is a ratio of whole numbers. They've just been modified by being multiplied by this decimal, 0.0974. So 0.0974 divided by 0.0974 is just 1. And then 0.285 divided by 0.0974, I get 2.926, which is real close to 3. And then I don't put ones in formulas, and this would be our empirical formula. So 2.93 is not as close to what I would want it to be for this type of problem, but it's close enough that we can round. Now, is there a substance out there that is CH3? Does CH3 exist? Turns out no. There is no molecule of CH3. The CH3 is unstable. It would require another H on there. CH4 is very stable. So what could this compound be? Well, if it's not CH3 because it doesn't exist, it could be C2H6, it could be C3H9. All of those exist. And that's how you get an empirical formula. Now, sometimes when you're doing empirical formulas and following this process, where you just take your masses and turn them into moles and then make the pseudo formula, and then you divide by the smallest number. When you do that last step and you divide by the smallest number, you get 1 for one of the elements, but you get a fraction for the other one. This sometimes happens. You get something like this. What do you do in this case? Do you just round? In this case, what you would have to do is you'd have to recognize that, okay, 1/5 is the same as 3/2, right? Well, if I multiply everything by 2, the result that we get is still an empirical formula. It's just the ratio is 2 to 3 instead of, say, 1 to 3. It is possible to have an empirical formula that does not have a 1 in it. It's not likely. However, there are molecules out there that definitely exist. Excuse me, with these formulas. So just be very careful when you're looking at your numbers and deciding, should I round or should I multiply? If you're real close to a whole number, just round it up. By real close, what I mean is like within 0.1. If you are not really close to a whole number, and you can see something that looks kind of like a fractional number, so fractional numbers would be like 0.5, or maybe 0.3, or 0.25, or 0.20, stuff like that. So in this case, you times by 3, and in this case, you times by 4, and then times 5, times 6, whatever, right? All right, so let's do an example where you actually have to do this, because we're going to get a fraction. All right, I'm going to give you this compound. It has chlorine and oxygen in it. Let's find its empirical formula. Just setting up Photoshop again real quick. All right, so same process. Oops. 16.80 grams oxygen. So we'll turn number of grams into moles. And it looks like I'm going to get like 0.3 or something. So 10.62, 35.453. Oh, yeah, 0.3. Look at that. 0.3, 0.2996. And then for oxygen, this is going to be close to 1. Grams of oxygen, moles of oxygen. Is that right? Yeah. Moles, oxygen. So we did the first step. We turn everything into moles. We're going to make our formula now. Obviously, no formula looks like this, so we're going to divide by the smallest number. That's this one. Why do I put an arrow there? Sometimes you get numbers that are really small and look very similar. I put an arrow next to the smallest one, just so when I'm writing the numbers down, I know which one I'm actually looking at. So I get Cl1O, whatever 1.050 is, divided by 0.2996. That didn't work out as... Oh, I times it again. Oh, okay, that's why. Wow, I'm bad at calculator, you guys. There we go. That's the number I was expecting. I ended up getting like 0.31, and I was like, what? That doesn't make any sense. Fat fingered the times button. Okay, so there's my ratio, 1 to 3.5. Obviously, you can't have 3.5 oxygens. That's doesn't make any sense. So to get rid of half, we'll times everything by 2. To remove the... I'll just write it as 0.5. Because 0.5 times 2 would be 1. And then 3 times 2 is 6, so add them together, you get 7. Now you gotta multiply everything, so that means that Cl becomes Cl2. And O3.5 becomes 7. And there's the answer. That's the formula of this compound. Now it's an empirical formula, so the actual compound might be Cl4O14. Or it might be Cl6O21. It's impossible to know without more information. All right. So now that you've seen these... Oops, it didn't advance because I got to click there. Now you've seen these, go ahead and try one for yourself. Or try two, actually. Here. So, in the first problem, I want you to tell me the empirical formula of this sample of mineral that has 25.28 grams of iron and 10.87 grams of oxygen. Type your empirical formula into the chat when you get it. And then the second one, we have a gaseous compound that contains 27.29% carbon and 72.71% oxygen. What's its empirical formula? Now, I'm giving you the percent by mass already, so what you can do for this problem is you can say, well, if these are my percentages, and I have 100 grams of it, then some amount would be carbon. 27.29% of 100 is just that. And then you can do the same thing with oxygen. You're going to get a really huge sample, but the math becomes easier. So if you're ever given a mass percentage, just do this strategy. Okay? Try these two problems. We'll go over the answers, and then we'll see where we're at, because we're going to run out of time pretty soon here. See you in a bit. 2 more minutes, we'll go over the answers. All right, let's go over these together. Gotta clear that. Oops, I hit the wrong button. That doesn't help anybody. Hold on. I'm moving things that I don't want to. There we go. Okay. Could not use the brush tool because the pixels in the group cannot be edited. Da 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 da. What did I do to my? Oh, I hit the wrong button. Okay. Good thing I have the history right here, just telling me like. All right, where did I screw up? So, 25.28 grams of iron, 10.87 grams of oxygen. All right, we're going to turn everything into moles. So a mole of iron is 55.845 grams of iron. So how many moles are in the sample? Looks like half a mole or so. 25.28, 55.845. 0.4527. Okay. We'll do the same thing down here for oxygen. And that's 15.999. And I get 0.6794. Okay. So we'll make our formula. Iron 0.4527, oxygen 0.6794. Ran out of space. This is the smaller number, so I'm going to divide by that number. Let's just try that again. I'm going to divide by that number. And when I do that, I get iron 1, oxygen 0.6794 over 0.4527. Oxygen 1.5. Well, I can't have a fraction, so I got to multiply by 2 to clear the decimal. And I get Fe2O3. Congratulations, it's rust. That's not a mineral. That's rust. Wow, wow, wow. Alright, I don't need the hint because we're going to solve this in exactly the same way. I'm actually going to move this over a little bit, though. So, again, if you're given a mass percentage, just turn it into a mass. And then you can do the empirical formula process. Turn grams into moles. So here I got 2.272 moles of carbon. I wrote the wrong thing. Hold on. Grams of oxygen. I'm going to cancel those out. That's going to be a lot of moles. 4.54. 5. I can already tell that these are like 1 to 2 here, so. I'm going to divide by the smaller of the two numbers. I get C. O2. There you go, and it looks like a lot of people got the correct answer. Even if you got CO2WU. Is that not how I'm supposed to say it, though? Or is it CO2-woo? CO2-woo. I don't know. Yeah, that's all. I think that's all the time that we really have here. So, we'll do molecular formulas tomorrow. There's really not much more in Unit 6, believe it or not. I've been had too, you feel? Oh. Oh, no. Well, I guess that's it. I guess I'll just, I don't have a, I was just gonna hit a button and, like, make everything dark, but I don't actually have that. Okay, anyway. I lost my train of thought there. I got lost in, like, a list of things here. So, that's all I'm going to do today. I am going to put on the announcement, though. So I'm going to open up quiz number 2 because we're done with Unit 2 finally. So quiz number 2, oops. Quiz number 2 due. Today's Tuesday, so it'll be due Tuesday, whatever week 5 is, so the 4th. And then on Wednesday, tomorrow, we're going to talk about lab number 2, because now that we've done molecular formulas and moles and stuff like that, you know everything you need to for lab number 2. So we'll do that tomorrow. But for now, enjoy the rest of the day. It looks like it's starting to become a pretty nice, I don't know, it just looks nice out my window. Is it as nice on the outside as it is on the inside? I don't know. Anyway, have a wonderful rest of your day, and I'll see you tomorrow. Take care.